graph colorings, this is another nice topic to work on your project in. Probably one of my favorite topics in graph theory are graph colorings. A lot of the research projects I've been involved with have involved graph colorings in some way. And we'll get to this in our class. We'll talk about this in a later chapter. Chapter 14 is vertex colorings. So we will get to this. But if you want to do your research project and get your project, get started on that, you can read ahead a little bit to graph colorings. They're not too hard to get. I'll give you a brief introduction here. Principally, the question in this topic is how many colors are needed to color the vertices and or the edges of a graph such that that coloring has a certain property. And so we're talking here about coloring the vertices of a graph, coloring the edges of a graph with certain properties being satisfied. We've already seen an example of this with bipartite graphs. Remember, bipartite graphs we could also define as graphs such that we could color the vertices using two colors such that no two adjacent vertices shared the same color. So bipartite graphs can be phrased in terms of graph colorings. So first off, our proper vertex colorings. This is a coloring of the vertices of a graph so that no two adjacent vertices share the same color. This is what we used for bipartite graphs. Bipartite graphs are two colorable. And what that means is we can use two colors to color the vertices and give a proper vertex coloring. So the main question in proper vertex colorings is what is the fewest number of colors needed in order to needed in order to produce a proper, fewest number of colors needed for there to exist a proper vertex coloring of a graph. So here I have the same graph twice. In this first coloring of the graph, so two colorings here. In the first coloring of the graph, I've used 1, 2, 3, 4 different colors to color the vertices. This is a proper coloring because no two vertices share are adjacent. No two vertices that share a color are adjacent. And in fact, all of these vertices have different colorings. So this is an example of a proper coloring of the graph. The question is, can we use fewer colors than 4? So this is a proper 4 coloring of the graph. Can we use any fewer colors than 4? And the answer is yes. We can actually use 3 colors and still get a proper coloring of the graph. So this is a proper 3 coloring. And so this is a principal question in this topic is what's the smallest number of colors needed in order to give a proper coloring of the graph? This parameter of the graph is known as the chromatic number of a graph, denoted chi of g. So here we're looking at k4 minus an edge, and so we can say that chi of k4 minus an edge is equal to 3. You can see that you can't do it with 2 colors. Any 2 colors I use, necessarily there'll be 2 adjacent vertices that share the same color. And so this is indeed the smallest number of colors you need. So that's vertex colorings, but you can also color the edges of a graph, and we encountered this in that first week of our class where we looked at Ramsey theory. I'll talk about that in a later topic. And so the idea here is very much the same, only we're coloring the edges, and a proper edge coloring is when no 2 adjacent edges, so 2 edges that share a vertex, cannot be colored the same. So here on the left hand side here, I have 1, 2, 3, 4, 5 colors used. So this is a proper 5 edge coloring. 5 edge coloring. And the question is, can I do better? Can I use fewer colors? And the answer is yes. We can actually get away with 1. There's blue and blue, red and red. I can actually use 3 colors here. So this would be a proper 3 edge coloring. And you can do a little argument here. It's not too hard to see that if I used only 2 colors, I wouldn't be able to find a proper coloring, right? Because I have a vertex here of degree 3, and if I only use 2 colors, then 2 edges that are adjacent to each other at this vertex would have to be colored the same, and that would not be proper. So the smallest number of colors needed to give a proper edge coloring. This is called the chromatic index of the graph, and that's chi prime of G. So here I can say that chi prime of K4 minus an edge is actually equal to 3. So that's proper colorings of both vertices and edges. So one place this comes up is in a very famous problem called the 4-color problem, which we'll talk about later on in the class. And so I'm not going to go into tremendous detail about it, but I'll give you just a brief overview and share with you an unsolved problem related to this. So this is the 4-color problem. The question is, can the countries of every map, real or imaginary, be colored with, so countries or regions of a map be colored with 4 or fewer colors so that every 2 countries with a common border are colored differently. And as we'll see, this actually translates to a more graph theoretic problem, which is that every planar graph, so every graph that can be drawn so that no edges are crossing, is 4-colorable. That is, we can give a proper coloring with 4 colors. This is the 4-color problem and the 4-color theorem. So this problem has already been solved. This is not an unsolved problem in graph theory. The solution to this does involve computers, and so there are some mathematicians out there that still want a solution to this problem that doesn't involve any computer intervention. But I think most graph theorists accept that this problem has been solved, but maybe some still want a proof that doesn't involve computers. So what's the unsolved problem here? Well, this is a variant of that problem, and it's called the Earth-Moon problem. By the way, I have links to all of these problems on the assignment sheet that I've posted to Brightspace, with links to more of a description of the problems there. So this one is found on the Open Problem Garden, but I'll state it here. What's the maximum number of colors needed to color countries so that no country sharing a common border have the same color in the case where each country consists of one region on the Earth and one region on the Moon? So this is sort of a science fiction take on the 4-color problem. What if every country on the Earth also has a region on the Moon associated with the country? They've claimed some space on the Moon. And so if you color that country on Earth with a certain color, you also have to use the same color on the Moon. And so the question is, can we still do this with 4 colors? That's an open problem. All right, so there's also the topic of total colorings. So we looked at proper vertex colorings, proper edge colorings, but there's a concept that involves both of these, and that's the idea of a total coloring. So a total coloring of a graph is a coloring of both the vertices and the edges of a graph at the same time. So an assignment of colors to the vertices and assignment of colors to the edges, such that the vertex coloring is proper, the edges are properly colored, and if a vertex and edge are incident with each other, then they too are colored differently. So that is, any 2 elements of the graph that are touching, I'm doing air quotes there, that are touching, have to be colored differently. The vertices, the edges, and every vertex and edge. The minimum number of colors required to produce a total coloring of the graph is called the total chromatic number of the graph, and it's denoted chi double prime of G. So that's the total chromatic number of a graph. So this is a fun one to look at some small graphs and compute their total chromatic number. And then there's an unsolved problem here, and that is, well, okay, so let me first give you an example of a total coloring. So here I have a coloring of the vertices and edges of K4. I've used, so red, so that's 1. I've used blue, 2, 3, 4, 5. Wait, did I count that right? Yeah, red, blue, green, yellow, magenta. So this is a 5 total coloring of the graph. Notice that any 2 vertices that are adjacent do not share the same color. Any 2 edges that are adjacent do not share the same color. And if a vertex and edge are incident with each other, they do not share the same color. And so this is a total coloring of K4 using 5 colors. Excuse me. The total coloring conjecture is that for any graph G, the total chromatic number of the graph is bounded above by the maximum degree plus 2. Seems like a fairly easy to state problem for total colorings, but this has not been proved. By the way, for edge colorings, the chromatic index of a graph is bounded above by delta of G plus 1. That's a solved problem known as Ising's conjecture. This, yeah, I mean, it's a nice theorem. It's not trivial, but it's proven. But we don't have a compatible one for the total coloring conjecture, or rather an extension to total colorings. So that's an unsolved problem. Again, this would be a great project to work on because you can look at some graphs, compute total chromatic numbers, and do some research on what's been. All of these conjectures, there's been some work, some smaller cases, some special cases that have been solved. And so this is great to go out and collect and see what other people have done, what mathematicians have done on each of these problems. All right, the last one I'll mention here in the coloring section is the rainbow Hamiltonian connection number. That's a mouthful. I mentioned this back in the highly connected graphs, and that's because this is sort of a mashup of colorings as well as highly connected graphs. So first off, define a special kind of coloring. A rainbow edge coloring of a graph is a coloring of the edges such that any two edges receive distinct labels, or distinct colors. Oops. Okay, so it's not hard to give a rainbow coloring of a graph. You just give a rainbow edge coloring of a graph. You just give every edge a different color. But you want this to have other special properties, and this is where it gets interesting. So take a Hamiltonian connected graph, right? Any two vertices, there's a path between the Hamiltonian path between them. A Hamiltonian connected rainbow K coloring of a graph is a coloring of the edges of G so that there is a UV Hamiltonian path whose edges are rainbow colored. And so you use K colors to color the edges of the graph, and between any two vertices you can find a rainbow Hamiltonian path. Of course, you might need a lot of colors in order to guarantee this. So the minimum value of K for which G admits a Hamiltonian connected rainbow K coloring is called the Hamiltonian rainbow connection number of G, denoted HRC of G. So this takes a second to get, but if you work out a couple examples, you'll get the hang of what this Hamiltonian rainbow connection number is. It's in general pretty difficult to find this number, but you should be able to do this for some small graphs, and that'll be good for the project. Now, what's the problem here? What's the conjecture here? So a little bit of background on this. One of my colleagues, Alexis Byers, who's at Youngstown State University, and my thesis advisor, we both have the same thesis advisor, Ping Zhang, who was a co-author of the textbook that we use. They worked on this topic and found the Hamiltonian rainbow connection number for many graphs, and in one case, a couple cases actually, an infinite class of graphs. So one class of graphs they looked at were the complete graphs box K2. So for example, if I take K3 and do K3 box K2, that looks like this. So that's, K3 box K2. I believe the Hamiltonian rainbow connection number for this graph is 6. And they were actually able to, this is a pretty impressive result, they were able to determine the Hamiltonian rainbow connection number for this entire class of graphs, Kn box K2, except when n was equal to 4. So let me go ahead and draw K4 box K2. So there's K4. Here's another copy of K4. And then we join up the copies. So here's K4 box K2. And again, the question, and they weren't able to figure this one out, but they were able to figure every other one out for n bigger than 4, was, again, what's the smallest number of colors we need to color so that we can find a coloring of the edges of this, so that between any two vertices, we can find a Hamiltonian path between those vertices that is rainbow colored. And that's the idea. Okay, so, oops, I've drawn this over my writing. So Professor Byers has since given this problem to a few classes of students, or a couple classes of students, see if anyone can get it for a project very similar to ours, but no one has found this number. So this is a very intriguing problem to try and find this Hamiltonian rainbow connection number of K4 box K2. Many have tried, none yet have succeeded. Maybe it could be you. One interesting aspect of this problem is that if you're very interested in coding or programming, since this is just to determine this number for a specific graph, you could try and write a algorithm to sort of brute force search through all the colorings and either find one that works. By the way, I believe this Hamilton, it's conjectured, is either 7 or 8. It's one of these two numbers they know, and so particularly interested in 7 edge colorings of this. So you might write a program to go through all of the possible 7 edge colorings of this graph, and then check them to see if they meet this condition of being Hamiltonian rainbow. Sorry, it's such a mouthful. A Hamiltonian rainbow 7 coloring of the graph. Now this just brute force, just completely brute force. I think there's too many possibilities for this unless you have access to a very powerful computer. You might be able to do it. So you might need to think about some tricks you can do for programming this. I think it's a very interesting programming problem if you're interested in that sort of thing. All right, so in the last one, I'll talk about Ramsey theory, and I'll see you there.